For this problem, we'll be focusing on the molecular orbital diagram for the cyanide ion. We're trying to determine the pi bonds and the sigma bonds of the overall bond order that's going to be formed from this unique ion. So before we get to the molecular orbital diagram, the one thing that I like to do is just draw the structure to make sure, the Lewis structure, just to make sure that I get what I'm expecting. So carbon has 4 electrons surrounding it for the valence electrons, while nitrogen has 5. And since it has a -1 charge, it'll have 1 extra electron. So I'll have 10 electrons to work with. So the carbon and the nitrogen are going to bond together, losing 2 electrons, leaving me with 8 more to go. So nitrogen is going to be more electronegative, so it'll get filled up first, which is going to lose me 6 electrons with 2 remaining. And I'll put 2 electrons on my carbon. And this compound is a negative, so I'll put a -1 there. Since my formal charge for carbon is going to be a valence of 4 minus 1 bond and 2 surrounding electrons, that'll be equal to a +1, while my formal charge for my nitrogen is going to be 5 minus 6 plus 1, which is going to be a -2. So I'm going to take one of my pairs of electrons and I'll form a double bond here to get me a structure that looks like this: carbon double bonded with nitrogen, and then pairs of electrons there, and a -1 charge, which will give me a negative charge on my nitrogen. However, this still isn't going to work for us, because even though I have 8 electrons around my nitrogen, I only have 6 around my carbon. So I will need to put another pair of electrons from my nitrogen in the bonding region, and what I'm going to end up getting is a carbon with a single pair of electrons, triple bonded with nitrogen, also with a single pair of electrons, and I'll have a -1 charge. That -1 charge means I have a formal charge of -1 on my carbon and no formal charge on my nitrogen, because I went from a -2 to a -1 and now to a 0 on my nitrogen. So if I was to just take this structure and break down from what I know, looking at a triple bond, I will always have 1 sigma bond plus 2 pi bonds. That's what I am expecting to see here. But when I go through the molecular orbital, the molecular diagram, I have to pay attention to what atoms are in play here, because based on the way my sp mixing is going to have different energy levels. And what's nice about this problem is that my carbon and my nitrogen both account for a very large sp mixing, and this essentially breaks down how I best organize my 2p my 2b orbital splitting. So I know that carbon is 4 electrons and nitrogen is 5. So rather than focusing on doing the molecular orbital diagram for my 1s, I'm going to focus starting on my 2s, because 1s is going to be filled up anyway. So when I take a look at my 2s orbitals for my carbon and for my carbon and nitrogen, I'll have an upspin and a downspin in my 2s, and then I'll have another upspin and downspin in my 2s for my nitrogen and carbon, which basically means I'm going to have an up-down in my first sigma, and my up-down in my second one. Now I did that wrong. Okay, I should have filled up the bottom one first, because the bottom one is my sigma 2s, and my top one is my anti-bonding 2s. So both my bonding and anti-bonding sigma bonds are filled. I got rid of 2 electrons from carbon and 2 electrons from nitrogen, so I have 5 more plus the negative charge, so I have 6 more electrons to work with. So when I now break up my next part, which is going to be my 2p's, based on the large spinning, my lowest energy is going to be my pi x, or the pi x. They said pi x and pi y is going to be my lowest, followed by my sigma 2p. Next step is going to be my anti-sigma 2p, and then my anti-pi x, and my anti-pi y. And carbon has 1 and 2, and my nitrogen has 1, 2, and 3, and then I'm going to have 1 extra carbon because of my ion. So this is all based on my organization on the energy splitting. So I'm just redrawing my molecular orbital structure here. I have an upspin and an upspin in my pi's, a downspin and a downspin in my pi, and then an upspin and a downspin in my sigma. So I've used up all 6 of my electrons here, and if you notice, I have my 2 pi orbitals filled and my sigma orbital filled here. And with all of this information, I can go in and start answering some specific questions about my bond order and whether or not this is paramagnetic or diamagnetic. So as you can see, I just went to a new slide and I just redrew everything that I had down. So when we talk about our bond orders, the nice thing about this is I can go ahead and ignore my sigma 2s and my anti-sigma 2s because according to my bond order, these two are going to cancel each other out, which is convenient for us. So when we first talk about our sigma bond order, I have 2 electrons in my bonding, nothing in my anti-bonding, and I'll divide this by 2, giving me a bond order on my sigma equaling 1. For my pi, I have 4 in my bonding, I have nothing in my anti-bonding, divide that by 2 gives me a value of 2. So my overall bond order is when I add my sigma to my pi bond, giving me an overall bond order of 3, since nothing is in my anti. As far as my unpaired electrons are concerned, everything seems to be paired up nicely, and if I can confirm that with the Lewis structure that I made earlier. So as far as unpaired electrons are concerned, none exist in this structure. This means that every subshell in the orbital has an upspin and a downspin, meaning that my magnetism for this problem is going to be a diamagnetic structure. So the key thing to remembering here for your molecular orbital diagrams, go ahead and draw a Lewis structure to get a vague idea of what everything should be in terms of how many sigmas and how many pi bonds and following the formal charges. But the key to this is recognizing what kind of splitting you're dealing with. It always depends on the carbon, the elements that are being used in the structure that you're creating the molecular orbital for. And you're also making sure that you're filling from the bottom up. So you want to fill up the bonding areas first before you hit the anti-bonding regions.